Welcome back. I've got a fun experiment for you today. It involves magnetism, and it's one that when I show it to my pupils, they're always really amazed by what happens. So, what we need for this experiment is three things and one slightly hidden ingredient. I've got a normal DC direct current lab power supply here. I've got a very strong magnet, and I'll just get the piece of iron out of the middle of it, and I've got a piece of copper wire. Now, the first thing that it's worth showing is that the copper wire isn't in any way magnetic. It isn't affected by the magnet. And I'm going to connect this copper wire directly to the DC power supply. I've got a loop of conductor here, and I'm just going to put it inside the big magnet. It's when you turn this on that something rather surprising happens. So, it's at this point you might want to pause the video and have a little discussion and a little think about what happens when I turn the power supply on. So, I hope you've had time to think about what might happen, so let's do the experiment. So, I'm connected into the power supply, and I'm going to turn the voltage up quite high with the power supply switched off, and then all I'm going to do is just flick the power button on. Did you guess correctly that the wire would come flying out of the magnet? It's most surprising. So, it's always fun, so let's try that again. We're going to turn the voltage up to full on the power supply, and then very quickly just flick the power switch on. 3, 2, 1, go. So here goes for the first part of the explanation. This was a bit of work done by a chap called Ørsted. I'm not sure I'm pronouncing him correctly, but he was a Danish physicist, or at least it's credited to him. I think some of the work was done before him, but it was forgotten about. And the story I always tell my pupils is he was mucking around in the lab with a compass, the type of compass you might use for navigation, D&V, orienteering. And then he probably just put his compass down on the desk and left it for a while. And then he started playing with some electrical equipment. And something quite remarkable happened. That the copper wire didn't affect the compass at all. It's not magnetic. So the two pieces of apparatus weren't in any way sort of communicating with each other. This compass is pointing to the north in my laboratory. But then when he played with his electrical equipment and turned on, the compass suddenly changed its direction. And when he switched off, it went back again. He noticed that as soon as he turned on, there was a force between the wire and the compass, and that disappeared when he turned off. If I turn the current around in the other direction, the compass will point in the opposite direction to the one it was then. So, we come to the logical conclusion that if a compass is magnetic and it's attracted to this bit of wire when a current flows through it, then wire carrying a current must also have magnetic effects. And it's this we're going to use to explain why the wire flew out of the magnetic field of the large permanent magnet. So, if there's anything your parents remember from physics at school that they didn't understand and always got confused by, it was Fleming's left-hand rule. A way of showing with your fingers which way the wire should go. I mentioned that the wire flew upwards in our experiment, but could actually be forced downwards. And it would be forced downwards if we turned the current around and had the current flowing in the opposite direction, or swapped this magnet around and had the magnetic field due to this in the other direction. So here goes for Fleming's left-hand rule. It's the one we use when we talk about what happens when conductors get thrown around in a magnetic field with a current passing through them. It's the one we use to try and explain how motors work. So this is my left hand, and some of you might remember our fingers represented different directions of things that were happening in this experiment. I always remembered when I was at school, first finger is field. So there's the north on my magnet and there's the south. They're not labelled so you can see them, but I've got some writing on top of them. So first finger field from north to south. The positive of the power supply has the current coming round from me through the magnetic field and back to the power supply. So this finger is the current, and my thumb, the thrust, is the direction that the conductor will be thrown upwards. So, first finger field, north to south, this finger current coming towards you guys, and thumb thrust upwards. So if I've got all of that right, all I need to do is turn on the power supply and switch on quickly, and out it goes in the direction I predicted. So I hope you enjoyed that experiment, and I look forward to seeing you again next time.